Welcome to this 15th lecture video for Physics 4A. We set aside this lecture set demonstrating a variety of types of physics problems we can now solve with the problem-solving strategies we have introduced so far: conservation of energy and momentum, and application of standard strategy. In this video, you will see the loop-the-loop problem, where you apply the conservation of energy problem-solving approach while using standard strategy to fill in the gaps in the given information. And we will cover two homework and worksheet questions, which illustrate the range of problems you can now tackle, and why you should continue to remember and apply what we have taught you earlier. Finally, the last two videos will cover exam-type questions, in which you use conservation of momentum in key steps. As with before, this is not a comprehensive presentation of all the types of problems that can now be solved. If I try to do that, this video would be more than 5 hours long. I encourage you to try other problems on your own, and also look at the additional problem-solving videos that are available elsewhere in the course. This is the track. I try to smooth it out so that it won't bounce around anymore. This is my ruler, and the ruler is assigned, it's glued to the background, and it's assigned to a no collision layer so that nothing will collide with the ruler. This ball will just fall through it. I guess what I wanted to demonstrate is how with a setup like this, if the ball falls right at this height, and let me make sure it starts out with a zero velocity, zero out its speed, that it doesn't actually have enough speed. As it rolls through, you will see that it doesn't quite reach that point, it comes off. And that's because for it to be able to do this loop-the-loop maneuver, it actually needs to reach this height with some amount of speed. So if I start with the ball here, then it should now have enough potential energy here to have enough kinetic energy here to not fall off the track and complete the loop-the-loop maneuver. So let me make sure its initial velocity is 0 and let it run. And yeah, just enough. It almost came off there, and it was just enough. Now, we will find an algebraic solution for this minimum height necessary in this following lecture video. At the conclusion of this derivation, we will come back to the algorithm simulation for an illustration of a real-world complication that we will come back later to address. So let me do it one more time. Same height, a little bit extra for friction, and it's not quite enough energy. So when you look at it carefully, it doesn't quite reach this height, right? So did we end with enough time to discuss why it didn't have enough energy to actually reach this point? We may not have. Okay, so let's just start with the question. So this is one of the things that you have to watch out for when you're applying conservation of energy. So let me diagram this situation here. So let me call this worksheet 7, problem 12. So the part that we are looking at in particular is the loop section. And we were hoping that the ball would eventually be at this position at some point, right? This is one of the snapshots we hope to have available. So let me call this snapshot 2. And we are trying to figure out, all right, so where does the ball need to start at snapshot 1 so that it'll be able to get to this position, right? And we are thinking about, okay, what's the minimum height it needs to start?
So we are thinking about what is the minimum energy the ball needs to have here. Good. Let me state the obvious things to get some things out of the way. So at a minimum, the ball needs to have enough potential energy to be here, right? Yes? So let me write down some of the parameters. So the radius of this track, let's say that's the radius r. So we would say, all right, at a minimum, we would say this ball needs to have enough potential energy. So its potential energy should be at least be its mass times g times the height, which will be twice the radius. Right? And when we made this guess, or when I made this guess, because I was running out of time, when I made this guess that maybe I could start at this height here and have it have enough energy to reach this position, what assumption was I making about minimum required kinetic energy at this position? Zero, right? Because I start this ball with a zero kinetic energy here. If energy is conserved, then I'm expecting this to get to this position with the zero kinetic energy. So that's what I was trying to state, that I was trying to say at this position, the ball will have minimum potential energy of this and minimum kinetic energy of zero. And that's a perfectly valid statement, valid description of a possible state of the ball. What the experiment is showing you is that that's not an achievable state. As in, so I was trying to see if I roll down the ball from here, that as it moves along this track, that it would eventually get to this position where the ball is here, momentarily at rest. And I guess, and that was somehow not an achievable state. Why do you think that state couldn't be achieved? As in, this ball never actually got to this position. What would you expect to see if I were to actually achieve this state, where the ball has this potential energy, as in it actually got to this position, and it has zero kinetic energy? What do you expect to see after that moment? It jumps straight down. Yeah, because I just release it from that state. It has zero velocity, so it would come straight down. Does that seem reasonable to you? I mean, reasonable in the sense that if the ball is doing this loop-the-loop, is that the motion you would expect to see at some point in that motion? No, right? So this is where your visualization skill is important, because it's really easy for you to simply write down this and think it's reasonable until you visualize what's going to happen starting from here, or what it takes to get to this position. This is one of the actually weakness of conservation law strategy. Because conservation law strategy relies on snapshots, it doesn't really guarantee the processes which take you to this point. You are kind of sort of either assuming that this snapshot will take place, or I guess what you really should have done is go through the sort of the imagination, visualization process to confirm that this is something that's going to happen. And then once you are reasonably sure that this is a achievable state, then you do the rest of the calculation. So here, where you imagine what this state looks like, that's when you realize, oh, it's going to drop straight down, and that's not a reasonable motion for something that's going through the loop. So that's where you realize, where I hope you should realize that this assumption here is wrong, that minimum kinetic energy is in fact not zero. It's going to have to be something else. So the minimum kinetic energy is something you need to figure out before you can proceed with the rest of this question. Yeah? All right, so I introduced this as a sort of the mixed strategy question. So for the first part, we are trying to start this with the conservation of energy. As in, we are hoping to come up with some kind of initial snapshot here. So let me call this snapshot 1. We are hoping to specify some initial conditions, some initial potential energy, And I guess initial kinetic energy will be 0. And we are hoping to specify this, say that energy is conserved, and solve for the, so we would be trying to say this starts out from some height, and we are hoping to be able to solve for this height here, right? So the expression that we are trying to set up initially had one unknown, the height. So in which case, we can set up the conservation of energy equation, one equation, and then solve for this height. As we are trying to apply that strategy, what we are beginning to find out is that I have one more unknown. So initially, I started out by assuming a particular value for the kinetic energy it needs to have here. What I'm discovering is that it's not 0. And whatever that value is, I don't quite know it yet. And with this additional unknown, conservation of energy, the way I was going to use it, is not enough anymore. So this is the question of problem solving. What do you do from here? So do you think conservation of energy is completely wrong, as in we have to scrap the whole thing and just start over from the beginning? Or do you think we will, at some point today, at some point in the next 10, 15 minutes today, that we are going to actually use conservation of energy at some point? Like it still has a role to play, I just need to bring in additional pieces. Right? Yeah, so I'm not going to erase any of this. I'm going to use that eventually. But what I now need to do is I need to bring in additional tools. I need to figure out, okay, what else do I need to do so that I can address this additional unknown right now? So what strategy do you think I can use to try to figure out this additional unknown? It helps to go through a checklist. How many problem-solving strategies have you learned in this class so far? So we have conservation of momentum. That's a possible strategy. What else? Standard strategy. That's the one that you use whenever you are analyzing forces. Did I teach you anything else? Energy. Yeah, we are already using energy. So that's in the list, but we have already used it. Or we are in the process of using it. So yeah, you really have two more strategies left that we haven't used it yet. I mean, maybe you could include the kinematics, but I don't see how kinematics will be helpful here, so let me fold it back. So it comes down to, all right, you have listed two things. Hopefully one of those two is useful, or you're kind of stuck in the, dead in the water. So, it's a 50-50 guess. Do you think I should be able to use conservation of momentum here, or standard strategy? Standard strategy. Here's a hint. This problem occurs in worksheet 7, where we have not yet introduced the momentum. So hopefully it doesn't require you to use the momentum. So yeah, you are going to have to use a standard strategy. So this is one way of guessing at it, just the process of elimination. Here's another way you could have figured this out. And it's a little bit tricky, because as you look at the situation, you are not realizing easily that there's a force involved in here somehow. And there's two different ways you can sort of get at the fact that there is going to be force involved. Any guesses what those two hints you can look at in the problem? Abdi?
Gravitational force?
I mean, the fact that there's gravitational force, now if that's the criterion, then there's no problem where you wouldn't try out the standard strategy, right? Because the gravitational force is involved here also. So it does have to be beyond that. Because when there's gravitational force involved, it's possible that you can address it by using potential energy associated with the gravity. So I want it to go a little bit beyond that.
Normal?
Why are you looking at normal force? Is there anything in the problem that hints at normal force? Stephen, are you going along the similar line?
Normal force is changing throughout, the direction is changing?
Normal force is changing, but I mean, there are a lot of problems that involve normal force. Like, as in, if this is just rolling down from here to here, that involves normal force. But if I wanted to find the speed here, I wouldn't need to bring in normal force to actually answer that. Because in conservation of energy, normal force is perpendicular to the displacement. It doesn't change energy. Steven, you had a...
Because it's going around the loop in a circle, therefore there should be a centripetal acceleration. Therefore,
Yeah.
force should be applied around
Yeah.
there.
So Steven says that the ball is going around in a circle. And that's actually a big hint, that this is a circular motion. When you hear circular motion, I want you to have this automatic association, acceleration. Whenever something is moving in circle, it's going to have acceleration, centripetal acceleration. Meaning, just from me saying that this is going around in a path like this, that already establishes, oh, there has to be acceleration. In fact, at this position here, this is going to be accelerating downward. Right? Otherwise, if it's not accelerating towards the center, then that's inconsistent with the fact that it's moving in a circle. So circular motion is a big hint that when there's a circular motion, that's going to involve centripetal acceleration, which involves identifying something as the centripetal force. And to sort of figure that out, you will probably need to use a standard strategy. And here's the second thing that this leads to. What force is this centripetal acceleration coming from? What are you identifying as a centripetal force? As in, let me imagine this. Let me imagine drawing, okay, now that we identify, all right, it involves acceleration, we're going to have to deal with the forces. Let's say we are now dealing with a free body diagram then. This is step number 1 of the standard strategy. So when the ball is over here in snapshot number 2, what are the forces on this ball that's going to cause acceleration towards the center? There's going to be gravity, which happens to be pointing in the convenient direction. Any other force? Yeah, normal force. So normal force is actually the one that plays an important role in all the other parts of the motion. Because when the ball is here, gravity points downward. So it must be the normal force that's providing centripetal acceleration. So in this position, gravity and normal force happens to point in the same direction. And this is where I hope you are thinking about the difference between where this is at just to the right minimum height. It should be around here. I was testing it out. When it's somewhere here, minimum height, versus when this is way more than minimum height. Because in both of those cases, this is still undergoing the same circular motion at a different speed, which means this centripetal acceleration, v squared over r, will be a different value. Gravity doesn't change. You need to have a force that you can change to give the correct centripetal acceleration. That's going to be the normal force. Okay? So that actually brings in a question which would relate to the normal force. So what do you think the value of normal force should be for the case that you are looking for the minimum speed of the ball, so minimum height that it's starting out at? What should the normal force be? Anyone have an intuitive answer? 0. Everyone intuitively thinks that this should be 0 at minimum? Yeah. And in fact, this is the second way you could have looked at this picture and figure out that you are going to have to deal with a standard strategy. As in, you imagine, once again, visualize the motion of the ball. So when I was trying out that first case where I was doing this, the ball did not stay in contact with the track. At some point, it came off from the track and fell off. And I don't know if the question actually mentions it. Sometimes it has the right wording to remind you of that. Sometimes it doesn't. So in this particular question, it says, yeah, it doesn't have, here. So when you look at it, it says, a skier wants to make a successful loop-the-loop, and here is it. That is, make it through the vertical loop without, this is the phrase, losing contact with the surface. And this is one of those, I like to refer to it as code words, because it's a matter of being able to understand the physics question a good chunk of it is being able to read word description like this and understanding what mathematical condition this is specifying. So description like losing contact with the surface, that actually has a very specific meaning that you can express it with a mathematical equation. What happens the moment sphere loses contact with the surface? False, okay. But there can be many different acceleration or velocity that the sphere can have as they are losing contact. I want to describe one particular condition that I can describe that will be the same throughout every single time somebody is losing contact with the surface. Asia. Yeah, normal force equal to 0. Because the normal force is the contact force. So whenever something is in contact with something, one thing you can say about normal force, it's not 0. Otherwise, it won't be at 0. Now, if something has completely lost the contact and never touched anything, then you can't quite say anything about normal force. But the moment something is losing contact is the moment that normal force barely goes to 0. So that's the condition, and it does take a practice looking at different problems and sort of making connection between this statement and that n goes to 0. But once you realize that, then you see, oh, this problem involves force. Then that would be the second path that would lead you to this exact same step. But once you get this far, once you come to this realization, then the rest becomes easy. It's a question of, can we answer this question? How much minimum kinetic energy it needs to have here? Or the equivalent version of the same question is, or what is the minimum speed at the top so that the ball here is consistent with this picture, where it's accelerating downward at g, and accelerating downward at g, since the normal force will be 0. Good. Okay, let me go through. So if you need to do it, then from here on you can do the full standard strategy if you want. This is step number 1. Step number 2, define coordinate axis downward, and I guess no components to break it down into. And then step number 4, write down Newton's second law equations. So this is a pretty simple situation once the normal force goes to 0. So let me skip to the step number 4, writing down Newton's second law equations. Then downward force of gravity, mg, has to be equal to the net force, mass times acceleration. But acceleration has nothing directly to do with the speed. How? Yeah, we have that it's a circular motion. So do that also. And so here, this v will be the minimum speed at the top. Minimum speed at the top squared over r. So that's it. Now we have enough information to solve for minimum kinetic energy. Then we can go all the way back here and solve for this height, which is what we wanted to find out in the first place. So let's go through this quickly. So mass cancels out. The whole thing doesn't depend on mass. Let me solve this for this minimum speed at the top. So the minimum speed at the top, actually let me solve it for this thing squared. Then it'll be r times g. Right? And I can use this to calculate the minimum kinetic energy. The minimum kinetic energy has to be 1/2 m v min at the top squared. Everyone here remember the formula for kinetic energy? Yes. So, all right. So this is so I can plug this in for this speed squared. Then I get 1/2 m rg. That's the minimum kinetic energy that the ball needs to have when it arrives at this position, so that it will be able to continue on and complete this circular loop. Good? Yeah?
When you write the velocity square minimum top equals to rg, where is that coming?
Yeah, this, so your Alice asking about where is the substitution coming from?
No.
Okay.
Bottom one. Next.
This one.
Yes.
Okay, let me write down the cleaned up version of this equation here. The cleaned up version of this equation is G, the far left side, yeah, equal to the right hand side. Yeah, let me finish writing it. V mean top square. By the way, I will skip some algebra steps, and that's partly because I want you to start practicing your algebra. In your entire science engineering career, your most important math skill will be algebra. So, I do want you to point out where my skipped steps confuse you so that I can do that. But what I want you to start doing is you have to be practicing algebra so that some of this can be done in your head. Yeah. Good. Okay. So that's the minimum kinetic energy. Now that's no longer a question mark. This is now a known quantity. So, in this problem, in the course of the problem solving, essentially you had to work out this mini problem here to answer one unknown that came up in the process of answering this question. Now that I have answered this mini problem, here's my answer. That means I can continue on with my previous problem solving. As in, I was going to use conservation of energy. Let's see if we can, finish the problem using my initial approach. Good? Okay, so let me write that down. So I'm going to try to use conservation of energy. So what do you do when you are trying to use conservation law strategy? So I wrote down, some stuff about potential and kinetic energy. Some stuff about potential and kinetic energy. Abdi, what are you saying I should do?
We're going to put the equation at the initial and then at the final.
What about, make that into an equation.
It's not show one and that's not.
Yeah. Yeah, so whenever you are using any kind of conservation law, so what you are doing is you are saying that you look at the conserved quantity, in this case energy, that the conserved quantity at one point, called this total energy at point 1, is equal to the conserved quantity at some other point, called this total energy 2. That's the very basic thing that you do with whenever you are applying conservation law strategy. That total energy at some point, if you are doing energy, is equal to total energy at some other snapshot. And the thing you have to pay attention to is, some of which was done here already. You have to answer these questions for yourself for a new problem. Is this quantity conserved? Is energy conserved? Is momentum conserved? And is this useful? As in, okay, let's say it's conserved. Will this help us answer this question? And part of doing this drill is something that I want to use some of the lab time for. So let's wrap up this question. We say, start out with this. Total energy at point 1 is equal to total energy at point 2. And I'm going to write this out. So total energy is potential plus kinetic. So at point 1, it'll be mgh plus kinetic. That should be equal to the potential energy at the point 2. That would be 2 mgr plus the kinetic energy. Now we don't say it's 0. We say it's 1/2 mrg. So plus 1/2 m or mgr. Let me do it in a way that's consistent. All right. So this is an equation, one equation with a single unknown. So we should be able to solve it. Let's go through that. Masses should cancel out. Oh, G cancels out too, because it's in every single term. Oh, that means I think I already solved it for H. It's a pretty simple algebra. So that's actually one of the reasons I like a conservation law strategy. The math involved in conservation law strategy often tends to be simpler than anything else you might see. So height, minimum height that I need to start out at is equal to 2r plus 1/2 r. I guess I should write it that way. 2r or 2 plus 1/2 r. So our earlier guess was 2r, that would give us enough energy. And what this calculation is now showing is that, well, I need to add a little bit of enough height in the starting position so that it'll have enough kinetic energy to keep moving here. So let's try that. So this is 2r, right? tell me where to start for 1/2 bar. About here? About here? Okay. I'm going to move it up a little bit more for friction. Because if I release it here, it's going to lose some energy as it goes down, so it won't be enough. So let me move it up a little bit here for friction. And let's see if it does the loop. Yeah, well, almost barely. So it's a matter of how much I need to account for friction. But okay, one thing I can say is if this starts out at 3R, that should definitely be more than enough. So this is about 3R, the height of the loop plus the radius. Good. Okay, let's start at 3R. And yeah, 3R is definitely more than enough. Good. So this is an example of problem where we sometimes call it mixed strategy problem. As in, you use conservation loss strategy, doesn't turn out to be enough, so you have to bring in other tools that are in your toolbox. And so
Now, back to the algorithm simulation for the description of the real-world complication that we will come back later to address. And the reason I wanted to do this precise setup is to show you one thing that's really difficult to show in a real-life demo. That is this. So with this particular thing, I set up really unachievable material properties. I made it a friction 0, and I made it restitution 0, so they don't always have any collisions, it won't bounce around. This part I'll just leave it be. I don't want it to bounce around still. But with the friction being 0, it does have unnatural motion. It slides down rather than rolling down. So the natural question is, what if this had been a ball, so that it actually rolls down, the way balls actually behave in a real world. So I'm going to put in some reasonable amount of friction so that it rolls down. Let's see what happens. Oops. This also needs friction. Okay, now let's see what happens. Okay, it's rolling, looks realistic. And now watch here. The height it was at, it wasn't enough. So at this point in the semester, we don't have enough tools to show you why it didn't have enough energy to get to that point. We'll get there in 2-3 weeks. So when we get there, we can return to this and add a little bit of additional height that will allow us to actually complete the loop for this spherical thing. So let me just do this as a kind of review, recap, or I guess an argument why you shouldn't forget standard strategy problem solving, even now when we are starting to introduce additional tools for your problem solving toolbox. So in this question, they say a sled plus a passenger has some total mass, let me just call that M, is pulled some distance, delta x, across the snow. Okay, there must be friction force at a constant velocity. Okay, that's probably meaningful. By a force, directed some degree above the horizontal. All right, so the question is asking about work done, and if you think about definition of work as dot product of a force with displacement, or if you have the or if you want to express what this dot product means, the magnitudes of the vectors times cosine of the angle between them. So in doing this calculation, you're going to need a force. And in terms of apply the force, you might feel like, oh, I know that force. Wait, I don't know that force. They didn't give me the force. So okay, I don't know the force. That's one. And when they ask you for the work of friction, I also don't know the friction. And oh, you know what? I think I can answer part C actually. Calculate the total work. This is something you can actually calculate right now. But maybe I'll leave that for the later. So actually, you don't know the first, and I think that realization should lead you to okay. I need to use a standard strategy. I need to figure out the forces, then I can apply the definition of work. So let me start out with the standard strategy. Step number one, I need to draw a free body diagram. So I'm going to treat the sled plus passenger as one object. And I'm going to say that one object has mass of m. And let me just think through all the forces. There ought to be gravity on it, but the sled doesn't accelerate downward because of the upward normal force. Um, and it said it's being pulled. Yeah, so I need to illustrate the applied force. I have some force applied that's being applied at some angle theta above the horizontal. And since they gave us the friction coefficient, kinetic friction coefficient, I should assume that there's a kinetic friction force, and that must be pointed the other way. Kinetic friction. Okay, and as always, I'm asking myself the question, did I draw all the forces? And it feels to me that way. And one of the things I need to check is what is the acceleration? And they say constant velocity. So that's a way of telling me that acceleration is zero. Oh, okay. All right. So the way with all the forces I've drawn, I'm pretty sure I can make the acceleration zero. So I think I'm good. I accounted for all the forces from things touching the sled, and that should be complete. Okay, that's step number two. I need to choose my coordinate axis, and I think with the acceleration being zero, I'm just gonna keep it simple. Use a straight axis. That also means I only have to break down one force, apply the force with this x component and the y component. Oh, and that's my triangle with angle theta. So my y component is going to be apply the force times the sine theta. My x component is going to be apply the force cosine theta. But don't get into the habit of always associating these with the y and x. You always have to check the triangle, use SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and all that. Okay, that's step number. So I did step number 2 and 3, breaking down forces into components. And finally, I'm ready to do step number 4, writing down my Newton's second law equation. So let's write it down. I need the two equations, one for the x direction, one for the y direction. So my net force in the x direction is going to be x component of applied force minus the friction force. F applied cosine theta minus the kinetic friction force. That's all. That's equal to 0 because 0 acceleration. Net force in the y direction is going to be, I have normal force plus the y component of applied force times the sine theta, and then I have gravity pulling it down, minus mg, and that's going to be 0 again because vertically it's not accelerating either. So before I close off my list of equations, I should check how many unknowns I have. I have applied force, that's an unknown, and I have friction force, that's also an unknown, and I have normal force, that's also an unknown. So I have 3 unknowns, 2 equations. I need one more equation, and hopefully it doesn't take you too long to realize, I need to express my friction force in terms of my coefficient of friction and the normal force. So with the kinetic friction, it's pretty simple. It's just the equality. You don't have to, worry about the things I tell you to worry about with the static friction. So, okay, I have three equations, three unknowns. I should be able to solve it. So I think what I'm going to do is let me eliminate normal forces. Then I don't have to worry about normal force ever in the remainder of the problem solving. So I think I'm going to solve this for normal force. N is equal to friction divided by mu k. Plug that in here. That gives me friction force divided by mu k plus applied force sine theta minus mg is equal to 0. By the way, I'm doing this a bit of an unusual order. Normally, we eliminate friction force, but in this question, we actually want to know the amount of friction force. So let's keep it in. I have a system of two equations, 1 and 2, involving two unknowns, and I should solve for both of them. Let me solve for friction. Yeah, let me do it this way. I'm going to solve equation 1 for the applied force. So doing that, I get 1 prime, which is going to be applied force is the kinetic friction divided by cosine theta. I'm going to reserve this for later. And then I'm going to use this to eliminate applied force from my second equation, solve that for friction force. So my 2 prime, after plugging in 1 prime, is going to be friction divided by mu k plus, now I plug this in, fk divided by cosine theta times sine theta, that's going to be times tangent theta minus mg is equal to 0. And I can collect like terms here. So this is friction force times 1 over mu k plus tangent theta minus mg. And I can solve for friction force here. My friction force is, all this is equal to 0. mg divided by tangent theta, just swapping the order, I don't like this coming first, plus 1 over mu k. Okay, I'm done. So that'll give me the friction force. And as I calculate the work of friction force, you have to be careful here. Wait, do I have to be careful here? You know what? I don't have to be careful here for the friction force. Because the displacement, the delta x, it's horizontal. So friction force, so with applied force, I would have had to be careful because I have to make sure I include this cosine theta. But with the friction, it's already directly opposite. So I'm going to have to remember the minus sign. But other than that, I can simply have this expression times delta x, or times 40 meters, and that'll give me exactly the answer I'm looking for. So let me do that in a calculator and plug in the answer to make sure I got it right. Let's do mg, 43 kilogram times g, 9.8, divided by tangent theta, so 25 tangent, plus 1 divided by 0.23. Okay, that's the ratio. And then I'm going to multiply that by 14 meters is equal to 1225 joule. So minus 1225 joule. Okay, let's plug it in and let's hope it's correct. Yeah. And now that I've got this answer, I can actually answer the remainder without plugging in any more numbers. The work done by applied force, I know it's 1225. And I could go back and do the calculation that I promised I would. I could plug in this friction force in here and then go through this work calculation. Oh, cosine theta will cancel. Oh, in fact, there you see basically the portion of the applied force that's doing work is going to be the same as the friction force. So that's another way to get 1225. And the way I got it is I already, before doing all the calculations, I knew the answer for total work was 0 joules. That's the work kinetic energy theorem. If it's moving at a constant velocity, then change of kinetic energy is zero. That means the net work done must be zero. So this is an answer that you can get from the reading the question and remembering work kinetic energy theorem from the start. So yeah, that should be it. And so this is really the hardest part of this question is doing that force analysis and figuring out the friction force or figuring out the applied force, figuring out the forces so that you can use that force to calculate the work done. Once you know the force, calculating work done is pretty simple. All right, so let's work through this. I think this is the last question in the energy worksheet. Conservation of energy number 3. It's a kind of a typical question with which we can demonstrate the use of the conservation law strategy. I think you might even have a homework question that's quite similar to this. So, hey, this is another example. So it says a 2 kilogram block is released 4 meters. Okay, I have this indication here. 4 meters from a spring that is fixed at the bottom of an inclined plane. Ideal massless spring has a force constant K. The plane is inclined at some angle theta. I'll be using letter theta for that. Assume that the plane is frictionless. Okay. So I think the question is trying to guide us through steps, although it's kind of unnecessary. So if you just want you to answer part B, you can just skip to that. And in fact, I'll show that to you in a bit. But let's just answer in order. It says, what is the kinetic energy of the block when it contacts the spring? So the block is eventually going to come here. 2 kilogram mass, traveled 4 meters to get here. So the very first thing, especially from the moment when you suspect, oh, I think I can use conservation law strategy to work this out. Once you suspect that, then the question you should answer is what quantity is conserved? And right now it's super easy. We covered only one quantity that could possibly be conserved. Here it would be the total and mechanical energy. And once you suspect the total mechanical energy might be conserved, then the question you have to answer is, are there non-conservative forces doing net work? And so when you consider free body diagram of the block, let me just draw it here, it does have non-conservative forces. Gravity, conservative, great, don't have to worry about it. But this normal force, it is conservative. But the reason it doesn't do any work is block is moving along the incline, which is perpendicular to normal force. So you're going to see normal force in a lot of situations where energy is conserved, but the normal force, a non-conservative force, it doesn't affect the energy conservation because it doesn't end up doing work. Because of this arrangement, when you calculate work done as the normal force vector times the displacement, this ends up being 0 because of this perpendicular direction. So, with that answer to the question, no, we know energy is conserved, yes. And once we have that far, then we are now ready to set up conservation law equation, one that will say total energy in snapshot 1 is equal to total energy in snapshot 2. And we have to decide what are our snapshots. I think it's pretty clear in this case. This is our snapshot 1. This is our snapshot 2. So we write down. Let me define my y-axis in this way. I'm going to define it such that this is y is equal to 0. So I really only have to worry about what is the height of the block initially, and at the end of the sliding it'll be at 0 height. Okay, so with that I'm gonna say my total mechanical energy is mgh for snapshot 1 plus the kinetic energy. It's being released from rest, right? So kinetic energy must be 0 in the snapshot. When it's slid down to this position, then its gravitational potential energy is 0. we expect it'll be moving at some speed v, mv squared. Good. So I think the masses cancel. It's the same mass. They cancel. And, oh wait, I don't want to cancel it because I'm not solving for v. They're actually just asking for the kinetic energy. So I think it's already solved. The kinetic energy is equal to the left-hand side, mgh. And I think you got all the numbers to plug in. Mass is 2 kilogram. G, let me use approximate value 10 meter per second square so that I can do this calculation without calculator. Oh, you're not quite done because I think if you try to look up h, that's not given anywhere. This 4 meter that they gave you, that's the hypotenuse, that's not the height. So you actually have to write out, consider this triangle. That given the hypotenuse of 4 meters and the angle theta here, this opposite side, you can get it using sine. Sine is the opposite over hypotenuse. So I can say, solving that for h, I can say h is equal to 4 meters, the hypotenuse, times sine of theta. So I can put this in for h. That would be 4m times sine of theta. And lucky us, I happen to know what sine of 30 degrees is. So if this is 30 degrees, then sine of 30 degrees is simply 1/2. So 4 meters divided by 2, that's 2. 2 meters times 10 is 20, times another 2 is 40. You have kilogram times meter squared per second squared. And this is the unit of energy that we call joule. 40 J or 40 joule. It's named after a guy who did a lot of work in thermodynamics. There are stuff in thermodynamics named after him, so he did a lot of work involving energy. So yeah, that's the kinetic energy of the block when it contacts the spring, 40 joules. And then it asks how much does the spring compress as the block is brought to rest. So there's a question you should answer, which is, as the spring collides with this piston, is energy conserved? And I think most people here have seen enough collisions, enough bouncing of the ball, that in this bouncing, energy is probably not perfectly conserved. Now, we are still going to use conservation of energy, and what authorizes us to do that is this statement in the question text. It says, the ideal massless spring. So for some of the energy to be transferred into the other objects colliding with it, they need to have their own kinetic energy. But if the spring and the whole assembly we assume is massless, then it can't take on any energy no matter how fast it moves. So with that in mind, we are going to say that at this step, energy is conserved. And once the block is in touch with the piston and they are moving kind of together, then as the spring compresses, it slows down. Spring is a conservative force, which means there are still no non-conservative forces doing work. So everything that we said before about total mechanical energy being conserved is still correct. Starting from here, and let me draw the snapshot here. So this would be a snapshot of where the box is somewhere here, and the spring has been super compressed. So even in this snapshot, let me call that snapshot 3, all the way from snapshot 1 through 3, energy is conserved. So really the only thing I have to do is set up this conservation law strategy equation again, and just to make sure that we are referring to the right snapshots. Snapshot 1, and I guess now snapshot 3. So let me draw that. And I think there's some bit of work that we have to do. So let's write down. In B, what we are looking for is how much did the spring compress? That's the question. And let's write down our conservation law equation. So the conservation law equation is total energy in snapshot 1 is equal to total energy. This time I think we labeled it snapshot 3. Snapshot 3. Okay, we break down these expressions as before. The total energy in snapshot 1 will be the same as before, mgh, and no kinetic energy. And total energy 3, I think you still have no kinetic energy, because we're talking about the how much the spring compress as the block is brought to rest. So at the maximum position, block will be briefly at rest. So we can say the snapshot 3 also doesn't have any kinetic energy, but it'll have spring potential energy in the form of 1/2 k times delta x squared. And here's something that has surprised a lot of people. There's a potential energy for you to worry about. It's a matter of how we define your reference. So if I defined my reference so that it's aligned with the relaxed or load-free position of the spring, then so this is where we are setting our y is equal to 0 for purpose of convenience in part A. What you are now going to see is you are going to see the block deep below y is equal to 0. So we have to worry about this this y, let me call it mean, because it's gonna be the lowest value of height in the whole setup. So this y mean position that it reaches, that's one, that's a non-zero, and two, I don't think we know that yet. So let me first write it in. So we already wrote in spring potential energy. Now we have to write in this gravitational potential energy that comes from the difference in height. So I'll say this is plus mg y mean. And as I do that, how I understand it is that because this is going to go below y is equal to 0, this is expected to be a negative quantity. And we'll just work with the numbers we get. So, all right, what question did it ask? It asked, how much does the spring compress? So they are treating delta x as an unknown. Okay, I hope it's just that unknown, although I don't think I'm gonna get that. Do they even give us mass? Yeah, mass is 2 kilograms. Okay, we got mass, we got g, we got h. Yeah, I think h is just given, or h is derived in terms of the 4 meters and the cosine, 4 meters and sine. I think that's all fine. And so 1/2 k, I thought I was given the value of k. Yeah, I'm given the spring constant. So delta x, that's I think our first unknown, because we knew mg h k, and delta x is the only quantity that so far we can express in terms of other known quantities. So one unknown, given that we have one equation, I'm hoping that that's the only one unknown. But as I'm saying that, I kind of know y mean is also an unknown. So we have one equation, two unknowns, and what that means is we really need additional equations. We have to think through the setup and try to see what information haven't we used. And I think if you're just looking at the question, this can be a tough question. I don't think there's any number here that you can directly use. The information that you should use is actually a geometric information. You know, imagine plotting this point blown up. So that point to that point, this is delta x, and this is, let me call that y mean, or minus y mean if we expect y mean to be a negative quantity. And I hope as you stare at this, you see a right triangle. And you can write down this equation that says minus y mean, the opposite side of the angle, is equal to the hypotenuse, delta x, times the sine of the angle. That's it. That's my second equation. And I think the way I wrote it, my second equation didn't introduce any new unknowns. So I can go ahead and solve it. So what are we solving for? So we are wanting to solve for how much does the spring compress. That is asking for delta x. So what I would say is that If you have more than one unknowns and you want one unknown, then counterintuitively, that unknown is the very last unknown you want to solve for. Because whatever I'm solving for right now, I'm going to eliminate it. So what I really should do here is to solve for y min, plug it in here, and then proceed from there. So solving for y min, I just move this minus sign over here by multiplying through by -1. So when I plug this in, this is the equation I end up with out of equation 1. Let me call it 1b. That's going to be mgh is equal to 1/2 k delta x squared, and minus, from this minus sign, mg delta x sine theta. So if I did everything right, this should be one equation b in terms of only one unknown. So we don't know y min. Did I not finish? Oh, wait, I eliminated y min. We don't know delta x. So I think I can solve for it. So in the right-hand side, I would... oh, wait. Okay, so I can solve for it, but I have to use quadratic formula because I'm seeing that this is squared, this is to the power of 1, and I don't see any nice easy cancellation that allows me to avoid using quadratic formula. So let me do it. I'm going to put this into standard form. Standard form is, in terms of applying quadratic formula, it's ax squared plus bx plus c is equal to 0. The reason we need the standard form is because that's how we all have quadratic formula memorized. The value of x that satisfies this is given by minus b plus minus square root of b squared minus 4ac square rooted 2a. That hesitation there is, it's been a while since I've used this because I've been trying to demonstrate use of SageMath. I think I've done that a lot. Let me do this one by hand. So I'm going to rewrite the equation into the standard form and then apply the quadratic formula. So let me rewrite it as 1/2 k delta x squared. And I'm basically collecting everything on the right-hand side and writing it as on the left-hand side. Plus minus mg sine theta times delta x, that's my x, and I've moved the mgh over, so it's gonna be plus minus mgh is equal to 0. So let's write it all out. We have what I'm saying is that delta x that satisfies this equation is given by that formula. So minus b, that sounds like a plus mg sine theta, plus or minus square root of, I'm hoping one of the two answers will be nonsensical, b squared, so that'll be m squared g squared sine squared theta minus 4 times, and then ac. A is 1/2 k, and c is minus mgh. So those minuses cancel, and yeah, so that's the quantity under the square root, and you need to divide it by 2a. So that would be 2 times, oh, so that's just k. Okay, let's, can I simplify it? Let me try to simplify it a little bit. I'm gonna say, combine it in this term, that's gonna be mg sine theta divided by k, and let me write down the other fraction plus minus, and I'm gonna absorb k into the square root, so it's gonna be k squared. So it will be square root of m squared g squared sine squared theta divided by k squared plus k will, well, it's k squared, so it'll cancel 1 out and then there'll be something remaining. With 2 times mgh over k, 1 factor of k having cancelled out. So I think as you look at it, you can figure out which of the two signs it should be. Should it be plus or should it be minus? And I think as you look at it carefully, I hope you will see that minus 1 work. Because this quantity here, that squared is basically this. So that plus this is greater. After you take the square root, that'll be greater than this. Which means that if you take the minus sign, the overall delta x that you calculate will be negative, less than 0. And I think in this context, that answer doesn't make sense. So that must be what you are able to obtain if this happened. As the block slid down, it kind of hooked with the spring, and after compressing it all the way down, then it bounces back. And whatever height it reaches, that would be described by the that would be described by delta x in the negative direction. We don't want that, which is why we are going with the positive sign, plus. Then, okay, so it's this thing plus that thing. Doesn't really simplify. You can factor out things like mg, but doesn't really simplify. I'll just leave it be. If you want, you can plug in the numbers to see what the delta x looks like there. I'll leave that for you for your exercise. It says the block continues to move up and down as it oscillates, and the block finally comes to rest and stays at rest. How much is the spring compressed? So this is the one question where you can't use conservation of energy. I think you have to realize that, as it says, the block finally comes to rest and stays at rest. You have to realize, the friction that we have been ignoring must have been significant in some sense over a long time period. That friction has taken out total mechanical energy. That's why it stops oscillating. So once you figure that out, then it gets to answer how much is the spring compressed. That's actually a force analysis question, and it's a little bit sneaky, but to answer part C, what you have to do is you have to draw the free body diagram of the block resting on the incline being supported by spring. So I think that'll help me draw all the forces. So I'll always have gravity, mg, and because it's on the surface, not accelerating into the surface, there must be normal force, and normal force is 2. So there must be normal force, and to keep it from sliding down anyway, that's the force being provided by spring force. So I think I can leave this for your Newton's law standard strategy solving exercise. What I do say is that after you go through the standard strategy and have spring force worked out, what we do say is that that spring force is equal to the magnitude of the spring force is equal to the spring constant times the delta x, the magnitude of the delta x. So once you have the spring force, then you can solve for delta x that way. That's part C. It's a bit of a sneaky question again because it's asking you for force analysis question in an energy conservation chapter. So how does the total energy of the block compare in B and C? So in C, it's lower. The energy in C is lower than energy in B because as it oscillates back and forth, to reach the state in C, it has some of the mechanical energy has dissipated into heat through the friction, work being done by friction force. So yeah, total energy of the block without calculating it, I know it should be lower in C. And you can do the calculation and double check. I'm getting this frictionless block sliding towards a ramp with some mass. So let me read the question. So the figure has been drawn here for me, so I won't redraw this figure. It says the block of some mass slides rightward at some initial speed towards the block of another mass, and the ramp is resting on a frictionless plane. That's the new part, and it's free to slide. When the block begins to slide up, the ramp begins to slide to the right, which you might intuitively guess. The question is telling you that happens. Assume that the block's initial speed is small enough that it will not slide all the way up. It will stop somewhere and then slide down. For each of the questions below, keep an organized record and attach it at the end. Okay. It asks, what maximum height does the mass M reach before it begins to slide down the ramp? So let me just sketch out the scenario. We are starting out with this setup where I have the ramp, which I'll take time to point out that its initial speed is 0. And I have the smaller block, which is moving at some initial speed of v0. And they are going to undergo what I would consider to be something like a collision. So as they undergo the collision, what I'm looking for is, so I call any kind of interaction that's a time limited collision, because that's the paradigm in which we are working for this conservation of energy and momentum problems, that as long as the interaction happens over some limited amount of time, then I can identify, call it a collision. Here it actually is, and try to identify snapshots that will be useful for me. So one of the snapshots that I think I need to identify is the snapshot where exactly what they describe happens. You know, the block small m has reached the maximum height on the ramp m, big M. So small block is here at m, and it has some height h. And this is the thing that you need to think through. So when this block has reached this height, how will this whole thing be moving? Because if you don't take the time to think through that, one easy mistake that a lot of people make is to say the final speeds of these blocks are 0. And then kind of work from that and use conservation of energy, get some height. And when and if you do that, you will find that the answer you get is wrong, because you have to consider two conservation laws. So far, we have covered the conservation of energy and momentum. And in any situation where these conservation laws might apply, you have to think through, is energy going to be conserved? And 2, is momentum going to be conserved? And hopefully as you read through this situation, especially with these frictionless planes, it gives you the sense that momentum is going to be conserved, especially in the horizontal direction. In the vertical direction, maybe they won't be conserved. Just checking time. But in the horizontal direction, there's no horizontal net external force. So the momentum should be conserved in the horizontal direction. And energy, especially with the frictionless things, I think energy is also going to be conserved. So I am probably going to use energy conservation at some point. So as you think through this scenario that's given in part A, really the key insight that when you arrive at it, it will allow you to answer this question is this insight. That when this mass m is at the highest height, it's neither sliding up nor down. So at that moment, momentarily, these two things are moving at the same speed at that particular moment in time. So that allows you to set up momentum conservation equation in a relatively simple way. So let me set that up. I can set up. So I'm trying to say net momentum initially. This is what I'm labeling as my initial situation. And it really is initial. And this is what I'm going to call final for now, which actually won't be final by the end of the question. The total momentum initial is equal to the total momentum final. And your initial momentum is simple. Only the small mass m is moving. So you can say small mass m times v naught plus 0 for the momentum of the ramp is equal to, and this is where you can simplify how you set it up. If you can treat these blocks as moving together at that moment in time, then it's the one and just one object of mass small m plus big M times, and you have the final speed v final. This is the unknown that you might be trying to solve for, except for the fact that the question is actually asking for the height. So if you're looking at this, you have one equation and one unknown, which is fine, except it's not the unknown you are trying to find. You want to find the h, which is entirely different unknown that your equation doesn't relate to. So you have to think a little bit more and try to get at, okay, how am I going to relate that h into some other things that I might be able to get at? And as you continue to think that, that's where you should realize, oh, energy. So far I got the sense that energy should be conserved in this interaction, but I haven't used the conservation of energy. So I'm going to try to use conservation of energy, where I'll say, okay, my total energy initially at the same point in the snapshot is equal to my total energy finally at the same point in the snapshot. So this is the part where it's a little bit different from the typical sticking collision scenarios you've solved for. In a typical sticking collision, your energy was not conserved. But here, somehow, you are going to include this gravitational potential energy and make it so that energy is conserved. So let's finish writing this out. My initial total energy will be the kinetic energy, 1/2 mv0 squared, plus the ramp has no kinetic energy. And then I have my final kinetic energy, 1/2 the mass of the combined thing, times v final squared, plus, and I'm going to write only the potential energy difference so that I don't have to get it into complicated expressions. The ramp, it doesn't move up or down, so it doesn't have any change in potential energy. This block M, it's going to be moving up a height h. So I'll say it gained gravitational potential energy of small m gh. So this is my second equation. And in introducing the second equation, I only introduced the one unknown that I'm actually trying to get to. So I have two equations, two unknowns. I should be able to solve it. Let me check the time. And I think in the interest of time, it's actually quicker for me to do the algebra by hand. So let me just do the algebra by hand. So I'm going to eliminate my final velocity, which I don't actually want. And just to get everything in terms of h or get everything in terms of known quantities other than h and then solve for it. So I'm going to plug in 1. So solving 1, I get v final is equal to m divided by small m plus big M times v naught. Plug that into 2, then I get 1/2 m v naught squared is equal to 1/2 sum of the masses times this thing. It's going to be squared. M squared over sum of the masses squared, v naught squared plus mgh. I see some things that cancel out. This cancels out. And actually one factor of small m cancels out of everything. So now I can solve for h by moving this term over to the left-hand side and then dividing by g. So I'm gonna do that in my head and then write it out with the h on the left-hand side. H is equal to 1 over 2g. I'm factoring out 1/2. And then I have a v naught squared minus this factor, the ratio of the masses, times v naught squared. Oh, I could have factored out v naught squared. But, depending on your time, you could just put in h is equal to 1 over 2 times g times v naught squared minus m over m plus m times v naught squared. Simplification, that's great when helps. I would never tell you not to simplify, but some things being left unsimplified, that's also fine. Especially given that we have a time limit. I have 9 minutes. Okay. So after reaching the maximum height, block M slides down the ramp and moves to left with some speed. Okay. Let me just copy this over so that I can save a little bit of time in building my argument. So we are now going past the scenario that was sketched out before. So this is still the initial. I think I can actually do that. But the final, instead of being the scenario that we had, we are now going to be in a situation where the ramp, I think it's still going to be somehow moving to the right with some speed, let me call it v2. And the small block, it has come down, and I'm going to assume it might be traveling to the left with the speed of v1. So with this scenario, let's read through the rest. It's asking continuous mode to right. Set up the equations necessary for solving these two speeds. Check and explain that it is possible. Okay, so I think through the conservation law strategies again, and as you think through it, hopefully you still have the sense that momentum is still conserved in the x direction, and there has been anything that would make energy not be conserved. So energy is going to be conserved again. So I write down actually basically the same set of equations, because I'm going to write down one for conservation of momentum, that net momentum initial is equal to net momentum final, which will now refer to this situation here, where two blocks have separated. And small block m is down back to the height it started out at. So we'll write an equation based on that. That'll be one equation. And we have a second equation that's going to come from energy conservation. I say total energy initially is equal to the total energy finally. So in some sense, we are doing the exact same thing in the part A, except what has changed is the snapshot that you consider to be final. And in this particular scenario, because energy and momentum is conserved at every step of the way, I don't have to break it up. I can just go all the way from the beginning to the end. So let me write this down. Actually, in the interest of time, I'll just write down equations here just directly. By conservation of momentum, so initial momentum is going to be m times v naught plus 0 for momentum of the ramp is equal to, and let me put in the signs into the equation. So I'll say m times minus v1 for the speed of the small mass plus big M for the ramp times v2. And somehow if I'm wrong about directions, then these will be negative somehow, and that'll tell me something. And the conservation of energy, initially I have the kinetic energy, 1/2 times m times v naught squared plus 0 is equal to, and I don't have any potential energy to worry about. It's just going to be kinetic energy again. 1/2 times m times, and I could say minus v1 squared. The minus will just cancel out, whether you put it there or not doesn't matter. Plus 1/2 times a big M times v2 squared. And I would argue that I have two equations and two unknowns, which would be v1 and v2, so this is solvable. That's it. Actually, quite simple. And the reason it's broken out that way is because 20 minutes is a really short amount of time, and solving this can take a little bit of time. So let me use, I think this is the one exception where Sage Math might actually do this more quickly than I can. So let me use my computer algebra system that I've taken a little bit of time to set up, mainly to just let it run. So I can define my variables, m, v0, v1, v2, and big M. I think that's everything. And my equation 1 is gonna be m times v0 plus 0 is equal to m times minus v1 plus m times v2. Equation 2 is gonna be 1/2 times m times v0 squared is equal to 1/2 times m minus v1 squared plus 1/2 times m times v2 squared. Let me just print my equations to make sure they are entered correctly. Ooh, what's going on? Yeah, they were not entered correctly. Okay, let's just try that again. Okay, good equations, and I can solve for those equations. Oops, equation 1, equation 2, and I'm solving for the two unknowns, v1 and v2. Let me put that into the solutions variables, and I'm printing it after solving. Okay, I get a set of two solutions. The first solution is what someone might call trivial solution, because trivial solution? V1 being minus, minus V naught because it corresponds to where nothing happened. They actually just pass through each other. It's the second solution I want. So I'm gonna use the CAS, and I'll just say from having used the CAS, this is the solutions that matches. And I will say, okay, that's my answer. I got 3 minutes. Okay, I can finish it. So yeah, and I could have gotten to this by hand. It'll just have taken a little more time. Using computer algebra system, I can get to this a little more quickly. I guess the one thing that I will see is that this V1, it could potentially be negative. And it would be negative if a small m is actually bigger than big M. So in the case where the ramp is actually lighter than this mass, it wouldn't actually bounce back. It would keep going in the same direction it was initially going. And if you've seen different elastic collision scenarios, you might have actually seen that in other scenarios. So, okay, results should show, okay, Roger. So this is actually one benefit of using computer algebra system. I can actually get my solution from the second element. It'll and I can plug in the numbers. So it says calculate what fraction of initial kinetic energy. Initial kinetic energy is equal to 1/2 mv naught squared. I'm doing this so that if I run out of time, it'll at least collect my partial work there. So, so what I need is I need an expression for kinetic energy of the mass, which is 1/2 times m times v1 squared. That's my kinetic energy 1. And in this kinetic energy 1, I can use a substitute syntax, and I can actually use it twice. But let me actually do it this way. So I'm going to first get this expression solution. The first element for v1, and I'm substituting big M is equal to 5m, and that'll 5 times m. And that'll get me, okay, that expression, good. So, and what I can do is I can get the expression for kinetic energy 1 and substitute in this expression. That'll actually calculate the kinetic energy 1 for me. Yep, that. Kinetic energy 1 of that. And how much time do I have? All right, 1 minute. I think I can actually do it here. So I'm gonna get the same thing, but for this time for the mass of the ramp, and I can put in my kinetic energy 2, which this time I won't bother defining. I'll just say that 2, substitute in that. And that will be what I put in here. Okay, K2 of m. And with that, I got 10 seconds left. So yeah, this is a kind of a long question, which is why previously I've only been able to do it partially, and yeah, so I will say here. In terms of my work, I'll say used computer algebra system. And I don't know computer algebra system is necessarily a time saver, especially with a tight time limitation like 20 minutes, unless you are already used to using it. What I would tell you as an advice is to focus on getting at least some partial answers, some partial response here. In fact, in D, I didn't actually fully answer it. I just gave these expressions. I actually need to wrap it up. So to finish out the K1 is, so taking the ratio in my head, it's 4/9 of initial kinetic energy of m. Um, yeah, and K2 it must be 5/9 of. Wait, would it be 5/9? Um, no, I've done something wrong. Is this 4/9? Let me just do this in on the side. So I have 2/9 um, times or divided by 1/2. That's 4/9. Um, so K2 should be the remainder of that, but might have messed up. Let's see. So M is that. Um, oh, I messed up here. It should have been capital M, not small m. So let me substitute in m is equal to 5m. Yeah, that's what happens when you do this in a hurry. So slight correction. Uh, Slight correction for K2. It should have been K2 of m is equal to this. So and to finish out that, it's a 4/9 of the initial kinetic energy. And that still doesn't sound right to me. In the limit where the ramp barely moves at all, the larger mass ends up carrying out less kinetic energy. Um, it doesn't feel quite right, but it might be that it might be that the limit where m is 5 times mass, it's actually not quite enough. So, but to finish this up, so the 5/18 divided by 1/2 is 5/9. So at least that's what one would expect. And the K2 is 5/9 of initial kinetic energy of M. Okay, so it says consider the ballistic pendulum shown below. The spring in the launcher is compressed, and when it is released, the launcher is stable. Yeah. Oh, this is the lab that you are doing this week. That's yeah. Um, yeah, I think yeah we did the conservation of energy lab. Yeah. Yeah. Okay. Um, the still ball is embedded into the catcher, and the catcher is applied. Assuming that the spring constant of the launcher is k, what is the launch speed of V naught of the still ball if the still ball was in? Okay, it feels like I can just use conservation of energy. Um, so what it's with all the information that they're giving, they're trying to give us the initial potential spring potential energy that it starts with. So we'll say, okay, my initial spring potential energy 1/2 k delta x squared, and it starts out with the zero kinetic energy. And at the end, all of that spring potential energy will be gone. It will be have transferred to elsewhere, and it'll have transferred into the kinetic energy. So we say this is equal to the final kinetic energy of the ball. And in this case, I'm just kind of shortcutting some of the steps in the interest of time, and also because it's particularly simple. So, so yeah, they're asking for this V naught. V naught is just doing the algebra in my head. Square root of k over m times delta x. Okay. Um, yeah. Oh, wait. Yeah. Still ball is a lowercase m. Um, Okay, if we imagine that the ball is launched and embedded in the catcher, to what height h does the stubble catcher assembly, right? Yeah, so this is the thing that you have to be careful about, and it's the subject of your pre-lab for Wednesday's lab. You have to treat this interaction in two parts. So there's part one, which will be the collision. So you have the catcher that sees the ball coming in with some speed, v naught that we calculated above, and this is going to get embedded. And once it's all embedded, they're going to be moving together at some speed. Let me call it v final. And in this interaction, we can say that the momentum is conserved. And energy is not conserved because it's a sticking collision. It's a totally inelastic collision. But we can use momentum conservation to work out this expression. You're not done there because it's asking what height does it rise to. So you have to work out part two, where you'll be reasoning through, okay, so I got this thing of some mass, m plus m, moving at some speed of v final. And it's going to be swinging up to some position at some height. And I guess this is how you should measure height. And at this height, its speed will be zero. And in this interaction, hopefully you have enough sense that energy is conserved because no non-conservative force does work here. The gravity is the only force doing any work that'll go into gravitational potential energy. Tension force, I guess in this arrangement it might be a little bit harder to see, but think as it's intuitive enough that tension force here doesn't work. So you have to work through that. Once you have worked through it, you'll have expression for h that you can relate in terms of other things you know. So I'm going to treat this v naught as a given quantity just so that my expression will be simple. I have v naught from part A, so I'll just use that. So let me work through part one. That will be the conservation of momentum. So I say my total initial momentum is equal to total final momentum. So total initial momentum is a small m v naught. That's going to be equal to the total mass, small m plus big M times v final. So v final is equal to ratio of the masses times v naught. Pretty simple. With these questions, the hard part is the conceptual part. The math part is actually pretty simple. That's what I love about conservation law strategies. Okay, energy conservation. So we start out with the total initial energy at the bottom here is equal to the total final energy. And we'll make things easy for ourselves and say that at this high, potential energy is zero. So I just have the kinetic energy initial. If I did write initial potential energy, that would be zero. The final energy, so at the top where the speed is zero, the final kinetic energy will be zero. And we'll have the final potential energy that we can write in terms of h. So initial kinetic energy should be 1/2 the total mass, sum of the masses, times the initial speed, which is confusingly labeled v final here. V final squared is equal to final potential energy. That will be the sum of the masses, g times h, labeled here. Yeah, what height does it reach? Okay, let me do a couple easy simplifications. Masses cancel. Um, and I think I see the steps. So I have h here. I want to solve for that. I don't technically know v final, but I can work it out from here. So, having done all that, in my head, h is equal to 1 over 2g times the mass squared. Wait, I did something wrong. Um, oh, no, no, it's fine. I think that's right. Yeah, yeah. Just make sure I didn't miss something. This is the problem of doing algebra in your head. Yeah, I think it's fine. So, when people don't do this correctly, I think this factor here, like if people mistakenly assume energy is conserved through the collision here, you end up coming up with a factor here that's not squared. It's supposed to be squared. Um, H is equal to 1 over 2 times G times mass squared over sum of the masses squared times V naught squared. V naught is from A above. Um, okay, the catcher is now modified to catch the steel ball with a spring-loaded assembly identical to. Okay, how does the height that the ball catcher assembly compared to? Oh, the answer here is actually simple. The answer is it doesn't change. Because really, when you go back and look at how we analyzed this part, we simply made no statement about energy. We didn't say it was conserved. We didn't say it wasn't conserved. So what matters is that the momentum is conserved, and with this new mechanical setup, momentum will still be conserved. So the fact that the energy goes into the potential energy of the spring, hey, that's great. We don't care. Because it so in working out post collision speed, all that matters is that the momentum is conserved, which it still is. So um, yeah, yeah. So okay, and in D it says even though they are identical, when the compression it's found the spring they always compress less. Explain why. And I guess the yeah, let me do the explanation first, and then we'll try to come up with that expression. So explanation it comes down to let's see. Um, so I think I should draw three snapshots. So you should visualize. I always recommend that you visualize a setup. So your setup started out with this kind of a snapshot where um, everything you had was in the spring potential energy here. So let me call this my snapshot A, where you had zero kinetic energy, all potential energy, max. And this fires, and you have a ball that's moving. All of this maximum potential energy went into here. So here's where you have maximum kinetic energy. And so this is my snapshot too. And now as this gets embedded, I guess this time with a counter spring here. So in this situation here, so you have some some potential energy in the form of the compressed spring, and from the answer for V final that we worked out up here, we know that this assembly is moving at some speed. So your kinetic energy here is not equal to zero. So in order to have some situation where the compression it compresses the same amount, you would need to have one where the kinetic energy goes back down to zero. And short of just supporting the catcher so that it doesn't move as it collides, it's not going to happen. Because really, while this was launching, initial momentum was transferred to the system, and until you take that out, it'll be required to have some kinetic energy. So so yeah, that's the reason. So let me put the explanation. Compared to the very initial setup in A, where all the initial energy was in the potential energy of the spring, the moment after the collision, the ball catcher assembly must have some kinetic energy consistent with the conservation of momentum, and this reduces the amount of potential energy available associated with the spring compression. So that's the explanation, and let me work it out. So the explanation also gives you some idea of how to express this. I guess since the setup was set up explicitly to make energy conserved, I guess we can start out with conservation of energy, because uh, now in this new setup, energy should be conserved. If it's not, then somebody messed up. So this is going to be my initial, very initial, and this is going to be my final. And I can actually skip the in between. Wait, can I? Yeah, well, because I already know V final, I think I can skip the in between step. um, Otherwise, I would need the in between step to get some sense of V final. Because from initial to final, momentum isn't conserved because of the act of launching. So total initial energy is equal to total final energy, and total initial energy was in the spring potential energy here, 1 half k delta x squared. I think that's all the symbols we used. Is equal to, now the total final energy that's split into two parts. There's the kinetic energy, 1 half the sum of the masses times V final squared, plus there's the potential energy, which will be the spring potential energy here, 1 half k and delta xc squared. Yeah. So yeah, everything here is known. I'm just going to treat V final as a known quantity since we calculated it up. Wait, I guess it's in the work, but so let me just say define V final is equal to m over n plus n times V naught, V naught from A above. Yeah, because I don't think I actually wrote out V final. Yeah. Okay. So yeah, let me just solve this for this delta xc. So doing the in my head. So slow down and verify I didn't make a mistakes, because there's a chance I am making mistake. Square root of delta x squared minus uh, k times V final squared. Yeah, and so this portion makes this less. Um, the amount to captures spring compresses is delta x c is equal to, it's lowercase c, is equal to square root of delta x squared minus divided by k times V final squared, V final defined above. And the dimensional analysis is a little tricky. Unit of K, it's got a lot of units. I think one of it, the units is kilograms per second. Squared, maybe. If that's right, then the unit here work out. Yeah, I think. Um, yeah.